Hey scholars, I hope you're doing well today. We are about to start a new unit on functions, just learning about some different properties, different types of functions. So we're going to start with these things called piecewise functions. It's basically a function that's broken up into pieces. So get ready to learn about piecewise functions. Make sure you're taking good notes, paying close attention. Let's get going. So piecewise functions are functions that are combinations of one or more functions. We can see three examples of piecewise functions. See how they're broken up into different pieces? All those different pieces have different rules and they make up one function. So the rule for a piecewise function is different for different parts or pieces of the domain. So the domain, remember domain is x values, right? So for this domain here, for these x values here, it has a different rule than from these x values from here to here. Okay, and we'll actually talk about this graph in just a second. So this piece on this graph, it's actually linear. Okay, all the pieces on this graph were constant. Remember that? Remember the constant family, what it looks like? Well, in this graph we have a linear piece, a constant piece, and another linear piece. Okay, and then for this graph we have a cubic piece and then a quadratic piece. All right, so different pieces of that function will have different rules. So let's explore that a little further here. So here we have a piecewise function. We have the equation form of it and the graph form of that piecewise function. So let's check out this equation first and we'll compare it to its graph. So over here on this side we have the rule, and on this side we have the domain. So the domain is the x values that it covers, right? And then the rule is, basically the formula, the rule that we have to follow along that domain. So this piecewise function is broken up into three different pieces. So, and we can see those pieces right here. This red piece right here, this blue piece right there, and that green piece right there. So when x is less than -1, we actually have the red piece. Okay, so you can see that as we go all the way to the left towards infinity, where x is less than -1, these are all the values of x that are less than -1, it's following the rule h of x equals x. So for this rule, h of x is going to be x. Okay, so that's that piece. And its domain is all the x values that are less than -1. Now, because it doesn't have that or equal to sign right there, we have an open dot right here. We have an open point there. Okay? Now, compare that to this blue piece. That's the next piece. It looks quadratic, doesn't it? This piece is quadratic, and you can see that the rule is quadratic, x squared plus 1. And that's defined over the domain x is greater than or equal to -1 and less than or equal to 2. So check this out. We have -1. It starts where x is -1, and then it ends when x is +2. So we can see here that those dots on the ends where x is -1 and where x is 2, those are filled in circles, aren't they? Because we have that or equal to part right here, okay, under the less than signs. So let's look at this last piece. It's going to be the green piece, right? It's constant, isn't it? We don't have a variable right here, do we? We don't have x right here. The rule is just h of x is -1. Oh, and let me label this real quick. That was h of x equals x squared plus 1. And this rule is h of x equals -1. So you can see that when the x values are greater than 2, so we're looking at the x-axis where they're greater than 2, the y values are always going to be -1. So h of x is always going to be -1 when x is greater than 2. Now, tell me, why is the dot open? That's right, because the value of x is greater than 2, but it's not equal to, right? If we had that equal to sign, it would be filled in. check this out. If these were to be filled in, what would be the problem? There you go. It would not pass the vertical line test, would it? Because we'd have two different values of y for that x. We'd have two different output values for that input value. Remember, for a relation to be a function, there can only be one output value for each input value. Well, in this case, we have two input values, two output values there. Same would go here. Neither of these parts would pass the vertical line test. But since they are open, they do pass the vertical line test. Okay? So, just wanted you to see that right there. Let's go ahead and move forward. Check this out. This is what we call a step function right here. A step function is a piecewise function that is constant for every interval of its domain. Okay, so constant meaning it looks like a flat horizontal line. So here's the equation of this step function. And this step function is comparing movie tickets, the price of movie tickets to age. So check this out here. This equation says the amount you pay, so f of x is 5, the amount you pay is $5 if you are in between the ages 0 and 13. Now, look at this graph. So we have age on the x-axis, so we would say this is the age, the domain is the age, and we have the price is the y-axis, right? So we have the price. The price is our rule, right? So if you are 0 years old, like basically you haven't been born yet, but as soon as you're born, you are you're just like moments greater than 0 years old, right? So as soon as you're born, from the time that you turn 13, you pay $5, okay? So we can see right here, 13 is not filled in though, right? So what this means is that as soon as you turn 13, and we can see that on that graph, and we can see that right here, as soon as you turn 13 years old, you are paying $9. So from the time you're born till you turn 13, you're paying $5, and then you're paying $9 as soon as you turn 13. Happy 13th birthday, right? Then you pay $9 until you finally get that senior citizen discount, and you get to pay $6.50. So $6.50. All right. So as soon as you turn 55, you start paying $6.50, right? $6.50 for the rest of your life. So this step function represents movie tickets. So we can see here that piecewise functions can represent real life scenarios. And this step function specifically represents how much you might. So let's try these. We're going to evaluate each of these piecewise functions for f of -3, f of 0, and f of 6. Okay, so make sure you follow along closely with me, see how I evaluate these. So I'm going to start off with f of -3. So what I have to do first is I have to look at the domain to figure out which rule I need to apply to f of -3. Well, so this is telling us the x value is -3, right? So this rule for the domain says that x has to be less than -3. Well, is -3, I'm going to substitute -3 for x here. Is -3 less than -3? No, that's not true. So we're not going to use that rule, okay? Because that is not true. All right, so let's try this next rule. So f of x will be 15 if -3 is less than or equal to x, and x is less than 6. So I'm going to substitute this. I'm going to substitute -3 in for x, and see if this is a true statement. Is -3 greater than or equal to -3? Yes, it's equal to, right? So we're going to end up using this rule for -3. Okay, this is the domain that it works for. It also wouldn't work for this domain, right, because -3 is not greater than or equal to 6. So here's what we're going to say. Since it worked for this domain, we're going to go with this rule. So when x is -3, the y value is 15. So f of -3 is 15. Now, we're going to try f of 0. So which domain is f of 0 going to fit into? Is it going to be the first domain, the second domain, or the third domain? Well, 0 is not less than -3. 0 is in between -3 and 6, though. Okay? So we're going to end up using the same rule for f of 0. F of 0 is going to be 15 as well. Now let's try this. F of 6. Let's figure out what f of 6 is. So which domain would this be true for? Is 6 less than -3? No, it's greater than -3. Is 6 greater than or equal to -3? Yes, it's greater than -3. But is it also less than 6? Is 6 less than 6? No, it's equal to 6, right? So this domain's not going to work. So neither of those domains work. Is 6 greater than or equal to 6? Well, yes, we just said 6 is equal to 6. So this is the rule that's going to work because this is the domain that works. So f of 6 is going to be 20. Now, check this out. Did we have any variables in these rules? Did we have any variables in those rules? No, we don't see x in any of those rules, do we? So this is going to be a step function like we saw earlier. Remember the movie tickets example? That was a step function. So this is an example of a step function as well. Okay, so let's move forward to number 2. So we've got g of x over here. Now, so we're not talking about f of x. We're talking about g of x. So all these need to change to g of -3, g of 0, g of 6. Okay. So we've got g of x equals 3x squared plus 1 if x is less than 0. We've got g of x equals 5x minus 2 if x is greater than or equal to 0. So we've got a quadratic piece if x is less than 0. We've got a linear piece if x is greater than or equal to 0. All right, so now we're going to find g of -3. G of -3. Well, we've got to check which domain does that fit into. Is -3 less than 0 or is -3 greater than or equal to 0? Well, -3 is less than 0, right? So we're going to use this domain. This is we're going to use this rule. So I'm going to substitute here. Here's what I'm going to do. I'm going to substitute -3 in for x. So 3 times -3 squared plus 1. Well, let's evaluate that. G of -3 equals, 3 times, -3 squared is 9. -3 times -3 is 9. And then plus 1. So 3 times 9 is 27. 27 plus 1 equals 28. So I'm writing this up here. G of -3 equals 28. All right. Now, we're to evaluate for 0. G of 0. So, G of 0. Let's see here. Is 0 going to be less than 0 or is 0 greater than or equal to 0? Well, it's greater than or equal to 0, right? 0 is equal to 0. So we're going to use this rule, 5x minus 2. So we're going to say 5 times 0 minus 2. We're substituting 0 in for x, right? So 5 times 0 is just 0, so we're left with -2. So g of 0 equals -2. I'm going to write that up here. G of 0 equals -2. All right, so last one, g of 6. Well, which piece is this going to fit into? Is 6 less than 0 or is 6 greater than or equal to 0? 6 is greater than or equal to 0. It's greater than 0, right? So we're going to substitute it into the linear equation again. So 5 times 6 minus 2. 5 times 6 is 30. 30 minus 2 equals 28. So g of 6 equals 28. Right. So this is how we evaluate piecewise functions. So when we substitute in here, this actually gives us points on our graphs. I'm not having us graph for this lesson, but we're getting points that we could graph. So the points that we would actually end up graphing on for the step function, the points that we got here were -3, 15, 0, 15, and 6, 20. The points that we got here for this equation were -3, 28, 0, -2, and 6, 28. So these were the x values, right? And these are the y values that we get out when we substitute those x values in. Remember, input, x values, output, y values. So these are the y values that we got out. Just wanted to run through some of those examples. Hope this was helpful in you understanding piecewise functions. Pay in a movie theater. So I hope this video was helpful for you in understanding piecewise functions. I know pieces of it, no pun intended, might have been a little bit confusing, but just make sure you come to class with questions and ready to learn. Good work today. Thank you, collegiate scholars.